Hi, and welcome to this first part of a three-part video that's all about metrology. Now, this is an introduction to metrology course, and that means that we're going to have to start out by introducing several basic notions. And, well, we're going to have to look at terminology. Now, this might not sound exciting, but it is very important. Now, we've been measuring all our lives, but there's a huge difference between general household or everyday measurement and accurate and reliable measurements like the ones that we need in a machine shop. And one of the main differences between accurate measurements in the shop and everyday household measurements is something called a tolerance. So every time we measure in the shop, we always ask ourselves, what is the tolerance of the dimension that I'm trying to obtain? Rather than jumping right into it and seeing, well, here's a micrometer and this is what it can do, and here's a steel ruler and here's what it can do. Rather than doing that, let's take a few minutes to understand the historic perspective of measurements in the shop. Measurements play a big role in our everyday lives. Almost everything that we do is controlled by some sort of measurement. I mean, all we have to do is think about the speed limit on a highway to know that measurement can have a huge impact on our lives. Historically, there's two main reasons that justified over our human history the development of measurements. And the first, well, is trade. Now, if you're going to be trading anything, the trader is going to want to know how much he's trading, and the tradee is going to want to know how much he or she is getting. So that was very important, and that probably led to the second reason, and that is science. In science, and in science I include manufacturing, well, in science there is a great need for accurate measurements of all kinds. One of the first recorded units of measurement was the cubit, and a cubit is the distance that separates your elbow from the tip of your middle finger. Now, note how attentive I am in the presentation of my middle finger here. It could be dangerous if I did it otherwise. But there is a problem with that, because, as was the case for most measurements prior to the 16th century, it was based on human anatomy. One way of getting around the variability problem would be to apply an average. And that's what they started to do to perform more accurate, or to obtain more accurate measurements. As an example, let's look at this royal proclamation from 1542, and it goes like this. On a certain Sunday, as they come out of church, 16 men shall stand in line with their left feet touching, one behind the other. This distance shall be the legal rod, and 1/16 of it shall be the foot. And why is that important? Well, it's important because it produces a more accurate unit of measurement. And that, well, is important because from one village to the next, you want to have something that's more or less constant. How does it do that? Well, it takes 16 feet. One of those feet is the longest, another of those feet is the shortest, and all the other feet in the 16 fall somewhere in between the two. But by adding those 16 up and averaging it to 16 equal distances, well, you get something that is a lot more accurate and constant from one town or village to another. Now, today in the machine shop, averaging is something that we still use. I mean, if I have a very accurate measurement to perform, I'll use an appropriate instrument, let's say a vernier micrometer. But I won't just measure once, I will measure the part several times, preferably at least 5. Of those 5, I'll eliminate the highest and the lowest. And the three left, well, I will average out to what should be the very accurate measurement required. Averaging out body parts isn't the best way to produce accurate measuring systems. I mean, it helped, but it wasn't the best. So what would be the next step in the increased accuracy world that developed? Well, the next step would be stable standards, and that means physical stable objects. An example of that would be to use a stone as the basis for a unit of measurement for weight. Physical objects are great, but they do have certain drawbacks. And the first, well, is there's just one original. So let's say you take a bronze bar and say that this is the basis for the unit of measurement as far as the meter goes. Well, there's just one. You can make copies, but every copy is going to be slightly different from the original. And that, well, is problematic. Another great problem with physical standards is that if they are destroyed, your unit of measurement runs amok with the disappearance of that standard. So what can we do to avoid that? To avoid that problem, we started using physical reactions rather than physical entities. Because if we base a system of measurement on a reaction, well, it's something that can be reproduced all over the globe. And that is why the bronze bar in Paris, that is the standard for metric measurement, well, can be described as that bronze bar. But the meter can also be described as being equivalent to 1,650,763.73 wavelengths of red-orange light in a vacuum. Historically, parts weren't interchangeable. I mean, they could be similar, but they weren't interchangeable. If we take as an example the wheel of a chariot. Now, if the wheel broke, likelihood is that a new wheel would have to be produced from scratch, or at least seriously modified to make it fit. That is problematic because if we go more global with the market, well, things need to be interchangeable. Well, the first step of that was really national interchangeabilities, because each nation tended to produce their own standards, and parts weren't necessarily interchangeable. That created quite a problem during the first global conflict, the First World War, and, well, it became obvious that global standards were required. So they were refined to become basically the standards that we have today, but they're always made a little more accurate with time. In the Second World War and up to today, most parts can be manufactured pretty well anywhere on the face of the earth and be interchangeable with other parts, and that is because of accurate measurement standards. Basically, you could say that our global economy just wouldn't exist if we didn't have accurate and reliable standards of measurements. Now, let's start taking a look at some basic principles and terminology. And we're going to start with direct measurements. A direct measurement is a measurement taken using a measuring tool that incorporates a readable scale. Now, the precision of a direct measurement is directly related to the precision of that tool. Steel rulers, micrometers, vernier calipers, and protractors are examples of direct measuring tools. So if you're going to perform a direct measurement, well, you need a readable scale. And a readable scale means interpretation. You have to read it. And when you read something, well, there's always a possibility of error. The second type of measurement is a comparative measurement. If you're using an instrument to compare a part to a standard, well, you're performing a comparative measurement. Comparative measurements are generally considered to be more accurate than direct measurements. They are generally considered to be more accurate because comparative measurements relate more directly to the tolerance of the part rather than to the dimension. And since there's no readable scale involved in this type of measuring, well, there's a much smaller chance of error. Sine bars, Joe blocks, straight edges, optical comparators are just some examples of comparative measuring tools. So a comparative measurement compares your part to something that you want it to be similar to. It won't give you a dimension, but it will indicate to you if it's the same or if it's not. A go, no-go gauge is a good example of a comparative measuring tool. Now, if we look at a go, no-go gauge for hole measurements, well, the gauge has two ends, a small end and a large end. If the small end fits in the hole and the large end doesn't, well, then you know that your hole is within its tolerance, but you don't know what specific dimension it is. The tolerance is also a very important notion to assimilate. And what is the tolerance? Well, the tolerance is the precision at which a dimension indicated on a plan must be respected. As an example of tolerance, let's say you have a dimension on your drawing that indicates 5 inches and its tolerance is indicated as being plus or minus 5/1000ths of an inch. That means that the part will be acceptable if its dimension is on or in between 4 inches and 995 thousandths and 5 inches 500 thousandths. Tolerances are very important because nothing is perfect. And we can waste our lives trying to produce a part perfectly. It's just impossible. There's always going to be some error included. The question is, how much error is acceptable? So if you have a part that has a very loose or large tolerance, well, you know that you don't waste your time using very accurate machining techniques to produce it. And on the contrary, if your part is very accurate, well, you're going to use accurate techniques, and that very accurate part is going to end up being way more expensive than the inaccurate or the part that has a loose tolerance. Another important notion is standards, and we've touched on this before in this video. A standard is what personifies a measuring system. And well, it's at the base of the system, so that means that it's from that standard that all measurements emanate. Now, in the shop, our standards are Joe blocks or gauge blocks. Both names mean the same thing. It is what we have that is most accurate. And since we calibrate all our tools using those gauge blocks, well, we ensure that our measurements will be acceptable and equivalent to the measurements performed in other shops. And that makes for part interchangeability. So standards are very important. Tool calibration from those standards is crucial. Surface finish is also an important notion. And it's a bit like the tolerance in that a fine finish on a part, well, it's going to be a lot more expensive than a rough finish on a part. So surface finish is how much roughness is acceptable, how much deviation or deformation of the surface is acceptable. So that being said, what is surface finish? Well, surface finish is identified on the drawing, and it's closely related to the operations you're going to perform. Grinding on a surface grinder will produce a much better or higher surface finish than milling on a milling machine would. So you have to choose the operation that will give you the surface finish required. Now, this is complex stuff. So surface finish and tolerance will both be covered and looked at in much greater depth in our series of blueprint reading videos. Another notion is decimal precision. And what does that mean? Well, when you're drafting or sketching, or even if you're reading a print, it's important to realize that the number of decimals indicated on a dimension has a lot to do with how precise your measurements have to be. It's an indication. So don't be putting decimals for nothing. If you want a precision that's equivalent to measuring with a steel ruler, well, in imperial, you'll be using only 2 decimals after the point. And if you want the part to be a little more accurate, well, and you want to use, let's say, an imperial vernier caliper as a measuring tool, well, a vernier scale, you will probably only put 3 decimals after the point. So if we go and use our calculator and we end up with 10 decimals, we round off to the number of decimals that will be representative of the accuracy that we're looking for. Oftentimes, human beings make bad decisions. And, well, one bad decision sometimes leads to another, that leads to another, that leads to another. And I guess we could call that multiplications of errors. But in the shop, that's not what we would say it is, because error multiplication is something very important in metrology. You do not want to measure from a measurement. Each measurement includes a certain amount of error. A steel ruler includes more possibilities of error than a vernier caliper. And a vernier caliper includes more possibilities of error than a micrometer, and so on and so forth. So if you measure from a point, which is our reference point, a dimension of 5 inches, well, that is accurate to within the measuring tool's tolerance that you're using. But if you use that same measuring tool and measure 5 times 1 inch, so 1 inch, and from that inch another inch, and from that inch another inch, and so on until you get to 5, well, you've multiplied by 5 the quantity of error possible. Now, if you're very lucky, each subsequent measurement cancels the error of the first, and you could end up at the end, if you believe in winning the lottery, with a very good measurement. But chances are that's not going to happen. So we want to measure once a distance from its reference surface, not several times to eventually get there. And that's called error multiplication, and it is something that we want to avoid. And for today, let's end with our 2 basic measuring systems, and that is imperial and metric. In the imperial system, the base unit is the inch. It is better or more acceptable to say 24 inches than it is to say 2 feet. The imperial system, however, can be either fractional or decimal. Now, the fractional imperial system, well, harkens or stems from a time when, well, calculators didn't exist and tradespeople just weren't well versed in math, because it's a lot easier to work with fractions than it is to work with decimals when it comes time to multiplying, dividing, adding, and subtracting. So that is where it comes from, and today it's still used, but more often than not it's used to describe overall dimensions or stock dimensions. In the decimal imperial system, well, we describe things in thousandths of an inch and in inches. So if we had to describe a dimension of 3.105 inches, we would say 3 inches, 105 thousandths of an inch. If there are 10 thousandths of an inch that come after, well, we add them afterwards. So 3 inches, 105 thousandths of an inch, and 5 10,000ths. As a general rule, the imperial system is considered to be a little more complex than the metric system. And that's because the imperial system has evolved over a much longer period of time. And when things evolve, like a measuring system, you have to add things to take into consideration the latest technological developments, so they get more complex. The metric system is much younger and a lot simpler. The base unit of measurement in the metric system in the machine shop, because it would be different for architectural work, in the machine shop it's the millimeter. So if I had 3 centimeters in the shop, I wouldn't say 3 centimeters. I would say 300 millimeters. And if I had decimals after the comma, because in metric the point doesn't exist, at least in Europe, in North America it's acceptable, well, I would just add those numbers on to the end. So let's say I had 300 millimeters and I wanted to add to that 15 hundredths of a millimeter. Well, I would just say it as that. I would say 300.15 millimeters or 300.15 millimeters. It's just that simple. So that's enough for this lesson. We'll meet again in part 2 of the metrology lesson, and we'll start by talking about linear measurements and the specific instruments that we generally use to perform them. And we'll also be looking at angular measurements and its specific instruments. So until then, have fun, be safe, it's so important, and happy machining.